va a empezar a ingresar a la gente.
Ya, porque ya vi que
Falta un minuto.
ya vi que Rubén tiró en YouTube. Voy a empezar a ingresar personas.
Sí, lo veo ahora, lo tengo, pero cuando quiero moverlo no me lo deja mover.
Teddy, si gusta, después de la sesión, me quedo con usted y le explico cómo colocarlo, el fondo virtual, porque es un proceso acá con la cámara.
Click to download acá. Ajá. Está bien, no nos preocupemos, después lo hacemos. Sí. Sí, ya lo tengo aquí, así que todo lo que tengo que ver es cómo bajarlo de acá.
Hola,
Sí.
hola, ¿cómo están?
Hola,
¿Querés
Andrea.
que
Hola, Andrea.
Hola, Andrea.
¿Cómo andan? Capaz que lo podemos compartir el archivo en el WhatsApp. Estaban en uno de los mails que había mandado Fernando.
Pero quizá en el WhatsApp se le complica un poquito más para ponerlo en la computadora, no sé.
No sé, sí.
Bueno, yo creo que ya vamos a iniciar, ¿verdad, Nancy?
Por eso no tiene sentido.
Señor, ya vamos a iniciar.
Ok.
Rubén. Buenas tardes. Continuamos con la plenaria Experimentación Remota a través de Internet a cargo del doctor Perry Tompkins. El doctor Tompkins es profesor de física e investigador en la Southwest Baptist University en Boulevard, Missouri. Es doctor en física y es un científico de instrumentación enfocado en la física aplicada con diseño y construcción experimental, adquisición de datos y control de instrumentos, utilizando múltiples soluciones de hardware y software. Así que con ustedes, el doctor Perry Tompkins.
Oh, wow, thanks. So can I share my screen? ¿Podría compartir mi pantalla?
Sí, señor. Vamos
Okay.
a ver.
All right. There it
Si
is.
gusta, nosotros
Ahora sí.
compartimos el video de acá.
Okay. ¿Está bien?
Right.
Okay. Gracias por la oportunidad para presentar unas. I'm speaking. I'm supposed to say it in English, so I wrote it in Spanish, but I'm going to speak mostly. But thank you for letting me have the opportunity to present on some work that we've been doing at SBU, some that has re-emerged because of the pandemic and our classes going virtual. So what I'm going to talk about is instrumentation, virtual instrumentation. And I'll explain what that is, because that's an important technique to be able to accomplish the main portion of my talk, which is remote experimentation across the internet. And so I will talk about during my talk why we are interested in this, what the definition, what the requirements are. I will actually run an example of the experiment and then talk about what we're working on, what's next, and then give conclusions. All right, so the technology that really makes this work is virtual instrumentation. It's a very strong technology. The idea is that you don't buy like an oscilloscope or a power supply or function generator and put it on the bench. What you do is you buy hardware that has the basic capabilities of measuring voltage very fast, generating voltage very fast for a function generator, measuring digital signals. Very basic functionality, although they can be very expensive and very fast in order to get a very powerful one. And then the way you form an instrument is by the software that you write that accesses that hardware and uses it and tells it what to do. And that's how you form an instrument it's a virtual instrument, even though it does have real hardware. So it's not a simulation. None of this I'm talking about is related to simulations. It is literally an instrument that you create with the software. And so if you want to change the software and run a different experiment, we have a number of experiments that use the same hardware in our first year physics labs, but has different software for every experiment. And so you just change the software. And you have limitations. The limitations are on that basic hardware that you buy, that basic data acquisition board or card or system. You have those limitations, but if you're within those limitations, you can pretty much do anything you want, create any kind of instrument that you want. So here's the three components of virtual instrumentation, or the main components. So you have sensors. You have something that's measuring something in the real world and turning that into a voltage, a digital state, or possibly a current. I don't have those kinds of sensors, but they're very common in industry where they actually use the current level to make the measurement. And then you have this thing I was talking about, this data acquisition device. And this is a picture of one that it's a new one to our laboratory. And I'll show you how we're building that into a housing so that it's easy to interface with it. And we're going to convert our first year physics labs over to using this particular data acquisition device. And of course, it has to be connected to a computer that has the software, in my case, LabVIEW. In most cases, I think people are using LabVIEW. It's very common. And you may or may not want to have that computer or need that computer connected to the web. In the case of what we're trying to accomplish in the long run, then yes, it must be connected to the web. This is just an example of a virtual instrumentation system. It's a vapor plasma deposition system, and the whole thing is controlled by one computer running software that controls all different kinds of hardware devices. It controls an RF power source, it controls valves, it controls other power supplies, measurement, all kinds of measurement devices, and it's all controlled in this software. And as I was developing this, then the folks would say, oh, could it do this? And my answer would be yes, always. But could it do this without buying more hardware? Many times that's true. Sometimes it'd be, well, you're running out of channels, and so we have to buy some more hardware. But in general, making it more complex and more user-friendly was something that we could easily respond to help them get this plasma system running. Now, the software that I use is LabVIEW. It's a fairly well-known software package. It's a 4th generation language for computer. It's a programming language, but it's very, very different from most programming languages. There is no text typing in. You actually draw your solutions. So for example, just to show you, so let's say I want to take I'll take a voltage measurement, come in, and I want to scale it. So I would just drop a little multiplication, wire the voltage in, attach, let's say if I multiply by 10, probably want it to be a floating point number, then the output now becomes the temperature. And so you literally draw your solutions in the LabVIEW. You don't type the code, which is in most, many other programming languages. And so as the next thing bullet says, it's really a lot closer to just drawing your solution or drawing your program than actually writing a program. This is made by NI. They've dropped the name National Instruments and now they're officially just NI for some reason. In Austin, Texas, ni.com is still the way to get to them. Okay, so just a little bit of background of what you can do with this. This is our teaching laboratory at my school. There's not a lot of students in here. This is actually this summer's class, but they are all holding an experiment on thermal expansion. And so in thermal expansion, you have to measure the temperature constantly, and you have to measure the length. They have long metal tubes that you run steam through, and you measure the change in length to get the coefficient of linear expansion. And the computer does that really well. We use the computer to take the dynamic data, but then the students have to take that data and extract the information. So here's L as a function of time. They have to figure out what delta L is. Here's T as a function of time. They have to figure out what delta T is, and then plug it in and be able to predict what material of metal that particular tube is using. So this is a new box that we're just designing this summer. This is going to have that earlier data acquisition device, but you can see we've programmed it. We've built it with banana plug inputs. On the other side, there are photogate inputs and a light sensor input. And if the experiment we're wanting to accomplish involves components for circuitry, then we have a breadboard, and most of the important signals are actually routed up to the breadboard. This is a box that we designed and printed on our 3D printers at our lab. And eventually we're going to use this box in place of a more expensive box that we want to dedicate to a junior level electronics laboratory. And the whole idea of this laboratory is to give them a teaching environment at our school that uses as much real authentic equipment as possible. And so all the programs that run not every experiment is computerized. Many experiments are static measurements, and it makes no sense to computerize something that's a static measurement like a force table. But those things that do have dynamic measurements, we use this LabVIEW software programs running and interfacing this same box. And we have about 14, 15 experiments that are all ran with the same box in just different software programs. We also are using this interface, although actually it'll be the other one I'll show you in a later picture, in our advanced labs and connect it to some of our advanced lab experiments. And we're just trying to expose our students to things that when they go off, and many of our students are pre-engineers, and so we want to expose them to the kind of techniques that they will actually experience when they get into a job or go on to grad school. Okay, so now for the main part of the talk, the remote experimentation across the internet. So what I want to do is create real experiments, traditional, not complicated. Personally, I don't have photon counting or some of the really cool things that are really good to put on there. But I'm focused on my first year physics students to have experiments that we can serve to them across the internet. All right. In this case, I only need one setup. And so I don't have to get 10 or 13 setups for the laboratory. I need one setup, and that helps the cost. And if other people use the same experiment, then they're not paying for that hardware, the equipment, they're only accessing it across the internet. For this reason, and for this to work well and fairly straightforward, I have to use LabVIEW and the techniques of virtual instrumentation. And by the way, we have students that have worked. Matter of fact, the one I'm going to show today was actually a student's senior project. So this is not for undergraduate students. This is not stuff that's way out of their reach by any means. They can easily develop these things. And I want my experiment to be controllable across a web browser. All right, so in order to do this, I have to have a completely remotely controlled experiment, everything. I cannot have operator intervention, somebody sitting at the table and changing things. I have to have motion control. I have to have power switches on and off. I have to have different things, but it has to be a remotely controlled experiment. If I have that, then, and I also need a fixed IP address. If I have, so that I can give it an address and it doesn't change its IP address, I can share that IP address with others. Those folks can just type in that IP address, go to the experiment and run the experiment. The host, the one that runs the experiment, has LabVIEW on it. It actually has a web server built into LabVIEW on the host. And so everything has to be done at that table at the experiment. But for a client, for somebody wanting to access it, they only have to download the LabVIEW, the runtime engine, which is free. They have to have a computer with internet access and a web browser. Now, there's only one web browser that today works, and that's the old Internet Explorer. And I'll talk a little bit more about that. But when I do that altogether, I have the real experimentation across the internet. All right, so the first experiment I want to actually demonstrate for everybody is just a simple experiment, the measurement of the magnetic field of a, well, officially it's an infinitely long wire that's got current going down it, and that's just the Ampere's law. Now, according to Ampere's law, the magnetic field makes circles around, concentric circles around a current carrying wire. Now, admittedly, our wire is not infinitely long, but I try to tell my students in my class that physicists and mathematicians have a different definition for infinity. Mathematicians' infinity is infinity, and physicists' infinity is it's too small, I can't measure the effect anymore, it's infinitely far away. And so that's essentially what allows this experiment to work. All right, so if I measure the current, which is straightforward, that's just a voltage drop across some resistor network. If I measure the actual magnetic field using a Hall probe as a function of the position, the distance from the Hall probe to the wire, and just measure that, I will literally get a measurement that allows me to determine the fundamental constant mu0, the permeability of free space. So I can measure that in the laboratory and get fairly good results. So this is just kind of a cartoon, and then I'll show a picture of what the setup. But essentially, I have a 475 watt 0.1 ohm resistor network. I have a 5 volt 50 amp power supply, and then a current carrying wire that moves over to the other side of the table. I have a magnetic field Hall effect magnetic field probe and on a linear stage that I can control. And I have power supplies, I have data acquisition devices. One of the things I have to power is to actually turn on the power supplies. In case I have lamps on the table, I'm not using them because we had our room lights on. But if someone happens to turn off the room lights, which I know, you can put a sign up and say, don't turn off the lights. And that doesn't mean somebody won't turn off the lights. So I have lights built in that are all controlled by a computer controlled power strip. So just to look at, this is what it actually looks like. So here's the network resistors I was showing you sitting on top of the power supply. And then here comes the wire, infinitely long wire going around in a loop. It's not infinitely long, but when I get 30, 40 centimeters away from the wire, all you can measure is the Earth's magnetic field. So these curves and the edges don't seem to make any difference. This is the controlling computer running the experiment. All right, so what I'm going to do is I'm going to switch over to a video. I do want to mention this is remote access. I can talk a little bit more about the fixed IP address issues that we're having right now. This is a group of students that were in London. Here's a group of folks that were in Ecuador that I was running the experiment for. Did that a couple times in Ecuador. And I've had a local high school teacher who has used this experiment quite often in his classes also. Oh, all right. So now let me switch to the video right here. And I'm just going to play the video and it'll explain why. Now we're going to run the simple Ampere's law experiment. Here is the experiment on a web page. And we're doing this locally within the same computer that runs the experiment because we still haven't got our fixed IP address repaired or returned. And so we can't actually offer this across the internet until that issue is solved. But we have the experiment, runs on a web page. This is using Internet Explorer, which is kind of an old web browser. But according to National Instruments, they are working on fixing that issue. But currently, only Internet Explorer allows the software to run and to embed the application, in this case, the experiment for the magnetic field. Eventually, they hope when they get around to it, LabVIEW will actually have a little bit broader access to the different web browsers that have been adding all kinds of security features in recent years. So what a person running this experiment would do is they would right-click on top of the front panel and request control of the VI. Once I've gotten requested control, the run arrow has now become solid instead of grayed out, and I can hit run. So for a laboratory to keep track, I just, in my case, I have put not so much a login screen, except for one part. You can hopefully I spelled that right. You can forego putting these in. I like to request people so I know who's running. I had a high school teacher that has run it a couple of times, and he makes sure that he lets me know when he was running it. One thing I've just added, and this is totally at anybody's choice, I added a key code. This grants permission. If you don't put in the key code correctly, it just stops the program. It doesn't let you actually run it. FISICA. All right, and so now what it will do, and in fact, before I go further, what it will do is, let me get to the desktop. It actually loads a document. It's an Excel, I call it history. And what it does is, you can see this is actually the run I just registered. And so it will keep track on an Excel for who's been accessing the experiment. All right, so back to the experiment. And now I can hit power on. And I have a 15-minute countdown timer because I'm running a 50 amp 5-volt power supply, which I don't want to overheat. Now, you probably can hear through the video the power supply had turned on, but what I've been to, you normally wouldn't be able to hear that across the internet. But what you can tell is that the current has gone from nominally 0 amps to 42.56. So it actually is getting 42 amps through this wire that's shown in this image. The image is live now, and you will see it once I start moving the stage. You will actually see the stage moving. Just to give you a little bit of a view, this plexiglass plate is holding the wire in place. This is a Hall effect magnetic field probe, and it's on a Parker stage that will allow it to move forward and backwards. So the first thing I do is I tell it to find the far stop. It may be overkill, but I tend to calibrate the stage every single time I run. That's how I coded this, so that it actually finds the two limit switches. It's going forward, and it's going to find the front limit switch first, and then it will go back and find the rear limit switch and be ready for me to continue with the experiment. So it's just about there. You can see the probe moving close, and as soon as it actually hits that limit switch, then it runs back. It moves slowly as it gets closer to the limit switch, and so that it's not overrunning the limit switch, and we don't have to worry about kind of smashing into it and not being where we think it is. So it moves slowly to the limit switch. Up here, the status message says it's finding the far stop and calibrating the stage. Once it's actually got to where it needs to go, the status message will go back and say idle. So it's still slowly moving back, and now it's gone to idle, and so now I know it's hit the far stop. Now, the first thing we want to do is we want to calibrate the magnetic field probe. What I'm doing is I'm 40, 50 centimeters, no, not centimeters. Yeah, I'm over 40 away from the wire. I'm going to call that zeros. So when I calibrate the probe, it'll go from an uncalibrated measurement to much closer to zero. So this magnetic field out here does have the Earth's magnetic field, but the Earth's magnetic field, depending on the orientation of the experiment, is pretty consistent from the whole motion of the magnetic field probe. And so I'm just subtracting out the Earth's magnetic field. The Earth's magnetic field is half a Gauss, roughly, and our maximum magnetic field we're going to measure is going to be around 50 Gauss. And so even though I have 42 amps, when you plug it in, U0 is so small that it will, just a single wire just doesn't make a lot of magnetic field. So now I tell it to pick the data points. So I'm going to pick data points. I always use the arbitrary. And if I say 0, which I tell my students they need to say 0, it will actually end the data collection touching the wire. Now, even though it's touching the wire, the distance from the active probe to the center of the wire is still 1.6 millimeters, and the software automatically adds that offset to every measurement. So 0, 1, 2, 4, 6, 8, 10, 15, 20, and I'll just do 30. Okay. You can have periodic. I've never used those. I put them in, but because we always want more data points as you get closer, it just tends to give us better data. Now I can just say, take measurements. You notice as I'm going down, I'm just working down this stack of control buttons. So I say, take measurement. Now it's going to move up. It knows where it is. It's actually going to go all the way to 0 and hit that front limit switch again, and then take the measurements in the order that I put them in. If I put the measurements in the reverse order, the program will automatically put them back to the smallest measurement first. Now, that's just because I want to go up and touch and hit that limit switch. I had to manually adjust the location of the probe once I have it at position 0 to make sure that the probe is where I wanted it to be. All right, so it's scanning. It's got 2 data points now. It has 0 and 1. It's moving to 2. You can see that our first data point is almost 52 Gauss. That is in Gauss. And it's dropping. And so we'll get the 1 over R curve as we watch it move back and take the data. Okay. There is a button here for a live frame rate. You could slow it down if you have so that it's only giving you 1 hertz of the images. If there's a limitation to bandwidth in the computer that's accessing it, I normally are able to run it at 10 hertz without any problem. You can see over here that it's talking about the last measurement. Now it's at 8 millimeters. I'm still at 13.3 Gauss, and my current hasn't changed much. We take a measurement of the current every time. It just barely changes during the experiment. And I have my students just do an average for the final calculation. So let's see, it's still moving back. When it's done, I show my students the data analysis, which I will show in this demonstration. They do not have access to the analyzed data. They can only save to a spreadsheet and then go and use Excel to recreate the analysis of the data. All right, so we're getting closer. I think I have 1 more measurement. And then the status message should go back to idle. Once it gets this final measurement. So now it's taking the measurement at 30. It's the final point. I'm at idle. The first step that the program wants you to do is to turn off the current in the wire. So you can see I've still got 42.15 amps. I turn off the power and the current will be measured and it's nominally 0. So just to see what the results would be like if I analyze the data with the program, of course I have it under a password. And there's the analysis. So you see the characteristic 1 over R curve. You'll also notice that there is not a point at 0, and that's because it's actually at 1.6 millimeters. But this is the distance in millimeters versus the magnetic field in Gauss. I linearize that data, do a least squares fit of a line, and I get, when I then take from that slope, which I mentioned earlier in my talk, I do a comparison with 4 pi times 10 to the minus 7, and of course make the conversions to all the SI units. This particular measurement, which is a 0.13% error, I can't say that it normally gets us 0.13. So if I hit done and I save to spreadsheet, now, normally, when I save to spreadsheet, once I get the IP address fixed, down here there will be a link that a person would just click, and it would upload the Excel compatible spreadsheet. I'm ready to go ahead and exit the experiment. If there are multiple people wanting to use the experiment, I would have to release control of the VI. And now you can have a number of people viewing it at the same time. Only 1 person at a time can have control. So if I'm in a laboratory full of students that are using this experiment, I would tell who can take control, and then when they're done, they release the experiment. Just to go and look at the data file, it's the same name. Every time it just writes over the data file. Here's the data file. Here is the distance in millimeters, the magnetic field in Gauss, and the current in amperes. And so now a student can take this in Excel, can linearize the data, do a least squares fit, and from the slope and the value of the current can measure mu zero, the permeability of free space. And that's pretty much everything for how it takes, what it takes to run the experiment. Okay, so let me go on and just talk about some of the next stuff that we're planning on doing. The next experiment, we're actually almost cheating because we already have linear motion completely under control for the magnetic field probe. So what we're going to do is hook up a diffraction and interference experiment. And so the phase one will be the easy phase. We're just going to have, we'll move the detector across, we'll have fixed slits, we'll have a laser. Those will all be controlled through a computer controlled power strip. Turn on the laser. We have to turn on a 5-volt power supply for the light detector and move the thing across, move the detector across using the exact same stage. So down below the magnetic field probe, we're going to put one of these light detectors along with a slit in, well, it'll have a detection slit. And then we don't have, like I said, we don't have control of what slit the laser's going through at first. And then we'll have a web camera so you can kind of see the things moving and making sure that everything's live. Then eventually what I'd like to do is put a rotary system right in front of the laser so that you could control and have a selection of double slits for interference or single slits for diffraction. That's going to be a bigger step because, well, first thing is I don't have a rotary system, but to make sure you get it lined up so that it works well, and every time it puts the pattern you want it to put at the detector. So that's going to be a little bit more work, but this first one, we really think we'll have phase one done before the end of the summer. So this is just showing a picture. Well, first, this is what the detector looks like over here. And it's got the smallest slit setting for this. It's a wheel, but we're just going to keep that. We're not rotating that. We'll have it on the smallest slit setting. And you can see the interference diffraction pattern. It's actually both. You can have diffraction without interference, but you can't have interference without diffraction because of the size of the slits that give you a really nice interference pattern. But you can see what it looks like. And this is from our traditional experiment. But what we're doing here is, so this is the magnetic field experiment we just looked at. And it's hard to tell, but there's the Hall probe and the wire. And so just down below the mount for the Hall probe, we will have this detector on there. And then we have just a solid state laser and a fixed slit, and then an optical bench leaning it. Now we still haven't, we're going to work on some fixturing. My student actually was talking to me today about, he's building the computer controlled power strips. And so that we have one for this experiment, but other than a little fixturing and getting things mounted, this one should be ready. And then the software. But the software will have a lot of similarities to the other experiment. And so we'll be able to reuse that software. Another strength of LabVIEW is that it's reusable code. Matter of fact, while I was showing the video just a minute ago, I was thinking, you know, when I do this experiment, I will now use periodic measurements. So I will take a measurement every millimeter or every 1/10 of a millimeter, and I'll take uniform measurements going across. So I will use that other part of my data. All right. And then the next one that we're planning on doing is sound resonance. By the way, this is a picture. This is a National Instruments Elvis 2 box. Those are the ones that we're wanting to take out of the first year physics lab so we can use those for they're much better suited to do an advanced electronics lab with those systems. So we're going to put the smaller, less powerful systems in the physics lab. And then on the sound resonance, it's just a plunger that moves a speaker and a microphone. So the speaker and the microphone can easily be controlled with LabVIEW and the data acquisition board that we're using on the other experiment. I will have to find a long motion, something on the order of at least 60 centimeters of motion, but it doesn't have to be precise. So we don't have to spend a bunch of money. We don't care about, you know, precision below 1/10 of a millimeter. So it would be, but it will have to move a long way as I move the plunger in. And as you can see on the computer, now this is the traditional way of doing this experiment, but as you move it, you just see the microphone picks up sound intensity as the sound goes through the different resonances in the resonance tube. So then the other thing is that anybody, once one of these experiments is set up, anybody could access it. This is showing all different classrooms in one country, but there's nothing that says it would have to be limited to one country, because now the internet is accessible. You have an experiment that's accessible across the internet, and anybody who knows how to get into it, if you put some sort of a key code to make sure people have permission to access it, then they can, you know, you can do those kinds of things, but make it accessible. So one laboratory could host a number of these experiments. Heather Lewandowski on Tuesday mentioned this as one of the strategies going forward as consequences of us being forced to go into more of a virtual because of the pandemic. She also mentioned that one of the strategies is to have real experiments across the internet. She also mentioned simulations. None of the stuff I'm doing here is actually simulations. They could be easily done using LabVIEW. I just haven't really done a whole lot with those. But multiple classrooms, they could be secondary, they could be other universities or high school, or other, you know, people accessing an experiment once it's made completely remotely accessible across the internet. So my conclusions for my talk, and I got, wow, plenty of time. So is that the LabVIEW runtime engine and web pages integrating, they function very well. It's very economical in the sense that one setup. Now, yes, I understand that LabVIEW is not inexpensive and the equipment's not inexpensive, but the thing is you need one setup for the laboratory, not one for each workbench, not multiple setups. Everything that I've done is using National Instruments data acquisition and LabVIEW. I know that there are other techniques, other softwares out there that can also do these things. And these are very accessible. I teach LabVIEW to my students. We're starting kind of a new program, but my students will be learning LabVIEW and DAC both at the sophomore level and at the junior level. And so by the time they're seniors, they would be able to use these and make their own experiments or do, you know, develop their own virtual instrumentation. I've actually integrated a lot of the virtual experimentation experiments, including the one I just showed you is in our laboratory manual for the first year physics. And so the students go through that experiment every semester. Okay, there's the solution. And these, they allow authentic experimentation. Everybody who runs the data will get different numbers every time. It's never the same because it's real experimentation. One other thing that I haven't done and would be a really good thing to do is to develop a clearer understanding of the errors in the measurement so that the students can put in the error handling into their measurement and get boundaries on the quality and such of their measurements. Okay, so I'm really ready for questions. But I actually wanted to mention one other thing. Well, since I was here, and my email address, if you don't want to ask a question, if you do, that's great. But my email address is on the screen. It's in the program, but you can email me anytime. Also, if anybody's interested, I'm still at what's called a Fulbright specialist, and that's a 2 to 6 week project. I'm sorry, that I could come if anybody's interested in having me come and help them with LabVIEW, with the virtual instrumentation, with remote experimentation, or 3D printing. And so that concludes my presentation. So I'm going to go ahead and stop share and see if there's any questions.
Les recordamos que todas las preguntas y comentarios las pueden hacer de manera presencial por medio, por ejemplo, levantando la manita del Zoom o también escribiéndolas por medio del chat. Existen esas dos formas.
Perry, you were talking about a single set of equipment and then accessible by a number of students. But can different groups access it at the same time? No.
No, you would have to have or audio.
Yeah. Should be
Now, different groups can, like when I have my students do it, I'll have 12 computers connected to the experiment. And they're all watching it happen as one table actually has control. And that's not limited to the people being in the same room. It could be at different locations. But yes, only one, because there's only one setup. And so only one person can tell it what to do. There's only one, only one person can tell it what to do at any given time. I'm looking on the chat. Marco Pacheco's was asking me about that box near the beginning with the proto board, and it's standalone, but it has a USB. So you just have to connect it to a USB computer. So that box that I told you that we 3D printed, that box has just a USB connection, and then the software tells it what to do. But there's no other interfacing. The interface, that USB dispositivo DAC that I said at that earlier picture, is inside that box. And then what we've done is we've put those connections on it to make it more laboratory friendly. The first year students aren't really excited about trying to connect wires, jumper wires up too much. So they can connect banana plugs or photo gates or something. I'm looking to see if there's any. Okay, and he's also asking about, it's standalone, but it's requires LabVIEW software or some software to interface with it. And it requires that box has about a $750 data acquisition device from National Instruments inside it. So the rest of it cost us, $30 to put together. But the big expense is that data acquisition device on the inside. And then everything we run is LabVIEW software. Now it can be, if someone was interested, it's not hard to, if you have a LabVIEW license, to make LabVIEw executables of the experiments, so that you wouldn't have to own a LabVIEW license to be able to use all the different experiments that box has been set up for. Okay, I'm going down. Okay, any other questions?
Hi, Perry.
Hey, Sergio.
How are you?
I'm well. I thought you were retired.
Okay.
You still doing work?
Okay, yeah. Oh,
¿No estás jubilando?
no, yeah.
Jubilado? Not yet?
Yes, I retired. Yeah. Okay, one question. You're a student, okay? The student say the law of the field camp, yes? Before
Studies Ampere's law?
Oh,
I'm sorry. They study
yes.
Ampere's law?
You're a student, okay? ¿Cómo se dice? ¿Conocen? Bueno, ya ni me acuerdo.
Preguntá en español que a lo mejor
Sí,
alguna cosa todavía.
a ver, Paul, a ver, Perry, tus estudiantes, your student, ¿ok? ¿Conocen de antemano las leyes del campo magnético correctamente para aplicarlas en las prácticas?
Well, bueno, lea en esta forma es un approximation, es un fácil. Now, mis estudiantes estudian la ley de Biot-Savart, mucho más complicado, pero este es un forma simple. Tengo dos formas de estudiantes. Tengo unos con cálculo y otros solo con álgebra.
Ok.
And los con álgebra tienen en sus clases, ¿sí? Pero los en cálculo tienen mucho más. Pero todavía es incluido en los dos clases y sí. Entonces, también no es un efecto muy grande, es muy sencilla, pero es un proceso para ellos para entender cómo medir el campo magnético, cómo hacer esta forma de experimento. Por eso yo dije que yo necesito adicionar propagation de errores.
Okay. Yes.
So, and I think con también es más fuerte.
Okay. Thank you.
¿Alguna otra pregunta que deseen realizar?
Mi nieto acabo de visitarme.
With a shirt of Uruguay.
Oh, sí. ¿Cómo se dice? Uniforme, ¿verdad?
Yes.
Yeah. Solo hace 2 semanas, sí, he usándolo.
Beautiful.
Gracias.
Beautiful.
Okay.
Daddy,
you still there?
Ok, si no tenemos preguntas o mientras alguien más desea formular su pregunta, les queremos comentar que en este chat de Zoom les acabamos de compartir los links de los talleres a los cuales ustedes deben ingresar ahora a partir de las 3:10 de la tarde. Si les recordamos, por favor, ingresar al taller en el cual ustedes se inscribieron. Eso es importante que lo tomen a consideración.
Ok. Muchas gracias.
Con gusto. Vamos a ver si tenemos más preguntas, comentarios que deseen realizarle al doctor Perry.
Sorry.
Yo tengo una pregunta, Perry.
Yo no tengo, solo adiós.
Mucho gusto, Perry, un gusto verte. Mira,
Dale,
es
Otto, sí.
fundamental en el experimento es tener un buen sensor de campo magnético. Y en las especificaciones de tu diseño, tú lo tienes para que podamos tomarlo como base para hacer los mismos experimentos, Perry.
Andrea.
Sí los tiene. A ver. Preguntarle de vuelta más lento.
Si
Hablale
quieres le pregunto,
lento,
Perry,
lento.
sí,
Es que nada más para avisarles que hay tormenta ahí donde Teddy dice que ha habido 2 apagones y que se quedó sin internet.
Sí, Teddy vimos que se tuvo que desconectar, sí, pobre.
Sí.
Por la tormenta. Bueno, dale, lento, háblame.
Despacio.
Para él.
A mí me interesa mucho crear ese tipo de experimentos porque nosotros resolvimos solamente dándole data a los estudiantes, datos, para que ellos con los datos y con alguna información pudieran realizar las experiencias. Entonces estoy muy interesado en poder tener, digamos, ese tipo de, por lo menos hacer la interfase. Entonces, tu proyecto está en algún lugar como para poder copiar el diseño, para que sea más fácil, ¿verdad? Para no partir de cero, para poder copiar qué tipo de sensor de campo magnético
sí lo tienes,
usaste y para poder acceder.
Perry,
eso.
Otto, explica que you have a link to begin with your device, okay, of field camp or camp field, okay.
Pero solo for the probe or for.
Okay. Link,
okay. Una cosa. Okay.
Yes.
Tuvimos antes una a fixed IP address.
Sí.
Cuando cambio a otro servidor de internet, perdimos estos todo. Mi IT folks me dijo que ellos están arreglando otra nuevo. Ahora mismo, Otto, no hay, porque no tenemos. Pero cuando tenemos el fixed IP address en el futuro pronto, voy a enviarte la dirección y las direcciones para arreglar su computadora. Necesita el runtime engine, pero depende y necesita lo mismo como mi software. So hay muchas varias versiones del software. Tú necesitas uno exactamente con mi software. Todos son gratis. Y Internet Explorer y después no hay problema. Ok, so estoy esperando para regresar mi fixed IP address. So cuando tengo, voy a enviarte. So tú quieres usar a través de la internet, ¿verdad? O construir.
Él quiere construir su propio dispositivo.
Lo mismo.
Sí, él quiere
construir.
Oh, ok, well, no tengo. Pero yo tengo más tarde. So tú tienes mi correo electrónico, ¿verdad?
Claro, Perry, claro, sí.
Me envié mi
envío.
Un mensaje. Voy a enviarte, pero todavía más tarde, solo tú y yo podrían charlar sobre estas cosas. La mayoría de cosas son very fáciles para encontrar y no necesita my stage para motion. los probes, Hall effect probes, muy fácil para encontrar. Una cosa es network resistors and the 5-volt power supply. Son muy difíciles. Estos son muy viejos. 30, 40 años viejo. Pero estos son muy difíciles para encontrar porque la mayoría de cosas usa solid state, otras cosas, y no funciona lo mismo. Pero charlamos sobre estos
Claro.
para construir.
Perfecto, gracias, Perry.
El taller de Perry nos lo perdimos por tener una conferencia virtual. En las presenciales, él siempre arma un taller con todos sus cables y sus cosas. Y es un poco más, resuelve más ese tipo de planteos, pero esta vez nos quedamos sin taller.
Mejor lo voy a visitar. Mejor te visito.
Te queda
Perry.
cerquita, Otto, te queda cerquita.
Sí, mejor te visito.
Sí.
Es que se nos volvió un problema porque sí estamos haciendo laboratorios, pero solo está basado en videos, datos y no tenemos esa parte experimental más directa, ¿verdad?
Sí, de acuerdo. No me gustan las otras formas, nunca he usándolos.
Perry,
Bueno, dado que tenemos alguna otra pregunta, María Andrés.
sí, sí.
Maite.
Perry, hola. Ya va, déjame prender la cámara para que veas que soy yo. ¿Hay acceso desde, por ejemplo, yo puedo tener acceso desde Venezuela a ese laboratorio? ¿O hay que comprar?
Sí. Well, wait, ¿para usar mi experimento?
Sí, para usar los experimentos.
Sí, no hay problema. Cuando tengo mi fixed IP address. Okay, so, sí, no hay problema para ninguna persona. Y mi experimento tiene una selección para tener solo 1 Hz de video. Okay, so no es demasiado bandwidth necesario por eso. Pero sí, Maite, no, creo que no hay problema. Pero, ok, so voy a hacer es cuando tenemos listo, voy a enviar todo el congreso la dirección. En cualquier persona le gustaría probarlo, es muy feliz para mí.
Perfecto, gracias, Perry.
De nada.
Bueno, dado que no tenemos ya más preguntas, entonces despedimos esta parte, no sin antes agradecerle al doctor Perry Tompkins por su participación en esta conferencia y por compartir con nosotros de toda su experiencia y conocimientos. Y les recordamos entonces que a partir de las 3:10 pueden estar ingresando a los talleres que ustedes se inscribieron anteriormente. Muchas gracias y nos vemos.
Hasta luego.
Luego.
Hi,
Perry.
Un gusto a todos.
Hi, Perry.
Sergio, Mario.
Okay.
Bye,
Kisses
all.
for your family.
And yours.